Here we go with session 2 of day 1 of the RNG Technical Symposium for 2025. I'm Paul Green. I run a biogas RNG advisory business, and I drive the biogas.tv website. This session, we're going to hear from PlanET Biogas to talk about completely stirred tank or CSTR digesters. You can ask questions on the fly in the chat or the Q&A box, and we'll also spend some time for questions at the end. Later today, you'll get an email from me pointing to the slides from this talk on my website, and a video recording of all the sessions will be available at biogas.tv by the end of the week. With that, I'll introduce Nils Hirsch from PlanET Biogas. Nils, take it away.
Okay, thank you very much for the opportunity, Paul, and hello everybody. It's a pleasure to present about continuous stirred tank reactors, or CSTRs, complete mixed digesters or other names. Paul, does everybody see my slide?
I think we're good.
Yeah, okay, great. So I'm Vice President with PlanET Biogas North America, and I'm with the company since 2019. Before, I have worked for Tidal Energy, Pioneer at the East Coast, and in product innovation. And those two are my passions as well, product innovation and renewable energy, or in a wider sense, to contribute to make the world a little bit better for us and future generations, at least to try. Right? And PlanET is in that sense a great fit for me. It's an innovative company. It's a key player in a sustainable sector, and it's small enough to be agile, but big enough to have some impact. So how did PlanET become that key player? We have been building a lot of long-lasting biogas plants, and we've gathered experience. I mean, we made mistakes sometimes. We improved, we optimized step by step, and we have been doing that since more than 25 years now, and closing in on 1,000 digester plants worldwide. I believe that a company is defined by its values and how it lives those values every day. And PlanET was founded by two engineers that are stemming from farmers' families. So it's not the two fellows here on the slide, just two colleagues with very nice smiles. And those two founders started building biogas plants for their families and friends. And you don't want to mess that up. And this customer focus is ingrained in the PlanET genes till the current day. Big value and very important value for us is climate protection. Biogas plants are a very powerful way to reduce CH4 emissions and tackle climate change. And that's a huge motivation for the team, for everybody in the team getting up in the morning, getting to work. Second value is respect. And respect has many facets. For me in everyday business life, it's really listening and being open and frank in conversations. And, sometimes I'm being asked why to choose PlanET, what makes you different, right? What makes you unique? And yes, we have a great technology and we have a lot of knowledge, but more importantly, we are truly interested in the customer's success and your success. We listen, we work out known and even more importantly, the unknown needs together with you. And then we develop the best suited concept for the project. And part of that is as well that if our technology is not a good fit, we will tell you. And if the technology is a good fit, and it's quite often that we have the right technology, then we work hard and design and build the best suited plan for you. And that's then the key value addition. So put your word where your mouth is. Those are our headquarters in Germany, and it was important for us to have a carbon neutral building using various renewable energies. We are a global company with facilities in Brazil and France and Germany, and we have a very, very strong local presence here in North America and in the US. Let's have a little closer look on North America. So PlanET has been in North America since 2006 with installations from coast to coast. We have 3 offices. I will turn on the laser pointer here. So we have 2 offices here in New York State and Ontario. That's where the company started. And then we have a 3rd office, a service hub here in Colorado that's in the middle of all the plants. We have 37 plants now operational in the US. and 15 in construction. And that adds up to more than 60 digesters delivered to clients in the United States in the last 3 years. And that in 10 states. You might have seen a press release a couple of days ago. We have more than 55 well-trained dedicated staff here in North America to design, deliver, and service your plant. This is just a snapshot on our bread and butter business. That's delivering great digesters. We have different technologies, high digesters and pancake digesters, all continuously steered. And we use, according to project needs, different materials from concrete over epoxy-coated steel and stainless steel. We have RNG upgraders as well. Two types, membrane upgraders and pressure swing adsorption. We define which one is used or which one is better suited together with the client, depending on the project. Usually we see the PSA, our PSA system, on bigger biogas flow rate projects, so bigger projects. We have delivered over 20 of those guys to North America in the last years. Service. So in addition to the material supply and construction support for digesters and upgrading systems, we provide services from start to end of the project. It starts with engineering in the early phases. It can be feasibility studies to find out if that's the right approach for the project or if the project makes sense at all. It could be finding out what's the best suited project location. And then through the entire engineering, detailed engineering, construction engineering, we provide support during the construction phase, technical advisory and commissioning services, and as well during operation, biological service, and technical service. And our vision is to be a partner at your site during all phases of the project and supporting you to make, and very important, to keep your project a success. So this is the last slide before I get into the more technical part of the presentation. When I had my interview in 2019 with PlanET, I didn't know anything about biogas. I was attached to renewable energy and interested in it, but I've never was exposed to biogas. So I thought it would be a good idea to do some research for this interview, and I found a diagram that is similar to this one. And I thought, well, biogas makes a lot of sense, right? It's baseload suited energy, and it looks pretty simple. And then I learned soon enough it's not that simple. It requires a lot of experience and technical knowledge and biological knowledge to design good plants. Biogas is very versatile in terms of output. It can generate various forms of energy, RNG, heat, electric power. It solves waste problems. It produces fertilizer. And key is to define the right technology concept for your project early on. Combine the right feedstocks, and we can design for a multitude of feedstocks and combinations. Feedstocks from ethanol plants, manure, food waste, chicken waste, sugar, you name it. And it's important to invest effort in this requirement research in the early phases, identify the needs. And that includes unknown needs as well that we will work out together with you. And the concept phase, I call it as well whiteboard phase. That's the most cost-effective phase to do changes in. And later it gets more expensive. When you have drawings already done, you have to redo drawings. When fabrication is started, you have to modify components. And worse, when the plant is built and operating, changes are very, very expensive. So you need to get the concept right. And that's one of the strongest value additions from my point of view of PlanET. We help you to get the concept right. So the agenda of the technical piece of it. So I will talk about CSTR digesters a little bit more. We'll give a snapshot on biology and feedstock. It's important to understand why CSTR is designed as it is designed. We'll share a little bit about the digester components, H2S control, a little bit about operations. Bernie will present in more detail later today. And close with service and some references, project references, if you have the time. If not, they are delivered in the slides that Paul will share. So when I started to set up this presentation, I'm trying to learn a little bit more about AI recently. I know it's coming. I know it's important. I know it will make our work life easier. So it's important to understand it. And I gave it a shot and said, okay, let's ask ChatGPT for a graphical explanation of a CSTR. And in word form, it came out pretty reasonable, right? You need an inlet for feedstock mixing mechanisms. You need a zone where you do the digestion. You have to collect the biogas, and you need an effluent outlet. So that sounded pretty good, pretty general, but pretty good. And then I asked ChatGPT to set up a graphic of it, and then this came out of it. So I cannot use it to explain in CSTR, but I wanted to share it here because it's pretty funny. I would say either it's way to go on AI still to get those graphics better, or I just used it wrong. But this is not how our CSTRs look like. They are far more simple in their design. So this is more how they look like. This is one example of a biogas plant in South Dakota. It's 4 digesters, 2.2 million gallons, pancake style. It's located at a dairy with 15,000 head. So that's the graphic I ended up using for the presentation. So explain high level the CSTR. So I compare it to preparing a soup. You have a pot, you have to fill the material in. So we feed from top and extract on the bottom. You need to heat the digester. You need good mixing to distribute all the ingredients very well. And then at the end, you have to take the gas out that's being produced. And in the pancake style digesters, you have 2 membranes. So first of all, you have the gas membrane. The gas membrane captures the gas and holds the gas back. It goes up and down with the gas level. And then you have a second membrane that we call weather protection membrane that protects the gas membrane from UV light and weather influence, weather impact. But it has as well another function. We are blowing air into the interstitial room between the 2 membranes, and that applies a gentle pressure on the gas membrane and gently extracts the gas and pushes it to the post-processing. And that's at very low pressure. It's a 0.03 psi that we have in those digesters in the pancake. A little bit about substrate. So that's the actual food for the microbes, and the actual material that is being digested. So what really stands out for me on this graphic is the big difference between the gas production capacity of the different feedstocks. And what is astonishing is that the dairy cattle manure, that's the basis for all those plants, dairy plants or dairy manure plants in the US, has actually very, very poor gas production capacity. And that is because of 2 reasons. So the gas is produced out of the volatile organic solids. It's digested by the bacteria and then produces methane and carbon dioxide. Dairy manure has a very low quantity of volatile organic solids in it. And then the quality is not that good because it was already digested in a cow's stomach. So that's why we have so low gas production here. And then at the other end of the spectrum, we have those feedstock like fat, very high total solids, very high volatile organic solids, but then the amount of gas that it can extract or that produce from a certain quantity of feedstock of organic solids is far higher. So that being said, this type of feedstock you cannot monodigest, but you can add it to a well-defined mix. The other aspect of the gas production is what you see in those curves here. It's biomethane potential curves and testing. So it basically evaluates how much gas you can produce or the bacteria can produce out of a distinct amount of volatile organic solids. And this is a typical shape of those curves. So you see it goes towards a plateau. And then this is the interesting area here for digester design, where you decide how much volume do I need, how much time do I have to give the bacteria to digest the volatile organic solids. And obviously, we don't want to have a 3rd or 4th digester for millions of dollars if we only have 2% more gas production. So this is very important to evaluate and to do some early on investment calculations and IRR calculations to see if the revenue pencils out with the CapEx and the OpEx. A little bit about biology. So how I explain it, it's going, bacteria are breaking down from big to small. And it's different bacteria at work here, and they are all at the same time living in the digester. And it's very important to balance those different phases. And I will talk a little bit more later on, but what you see here, the bacteria of those early phases are breaking the material down to acids. So they are reducing the pH, and they like to have a little bit lower pH to live in. It's between 5 and 6 for those two bacteria groups. The methanogens, those bacteria that we like because they produce the methane at the end, they like higher pH, around 6, higher 6 to 7. And they have the slowest reproduction time. That's a very important consideration as well. Those guys here, reproducing very quickly. If they get good food, they become too many. And these they need more time. So this is all to be balanced. And this plays a role in my further explanation. So tank dimensioning. I have to define how much I can feed, how much volatile organic solids I can feed at a given point in time per digester volume. And you see that there are different ranges, and it's not a lot. It's like feeding your pet, right? You cannot give the pet too much. It would eat everything, and we would basically destroy the balance in the digester. And those are typical quantities what we see for organics, 0.3 pounds per cubic feet digester volume per day. And we have some monodigestion where we can go higher, close to double that amount, 0.6 for in specific cases. But you have to need a very close look and analysis on that. TS, so total solids, it goes a little bit along with the organic loading rate. If the VS, the volatile solids quantity, is high as well, you want to get as high as possible here, but you have to consider as well viscosity limits and mixing limits at this one. So if I push those two values here, I need less digester volume, less digesters, less CapEx, but I still need to have a stable process. Same with the retention time. If I give the bacteria more time to digest the material, I need more digesters, more volume. You have to be careful with that. Usually we want to be pretty tight on retention time. Total nitrogen, that's another design consideration that we have, especially if we have feedstocks with higher protein content. We often have a nitrogen issue. But here we have some wiggle room here as well, because, I mean, obviously we can dilute, but then we get bigger digesters or more digesters, more expensive. You can always dilute, or we can do ammonia stripping, but that equipment is very expensive. So you want to be very careful with that as well. If we are really at the tipping point of those 6.5, 7 kilograms per metric ton, we can look a little bit deeper into how we operate the digester and can change the temperature profile a little bit, or the pH, because NH3, so ammonia, is more toxic to bacteria than the ammonium ion, the NH4+. And if I have lower pH and lower temperature, I have less of the NH3 and more of the NH4. So if you look into the free ammonia nitrogen, you can fine-tune a little bit the digester, and you might get away without ammonia stripping, or you can save a little bit digester space. So it's very important to consider as well. A little bit about the different digester types. So we do both tall digesters and pancake. Both have advantages and disadvantages. Nothing in the world is perfect, right? So it's always a balance. Tall digester is very nice for bigger liquid volume on a smaller footprint. We can go bigger. We can go up to 2.7 million gallons for those tanks. A downside, less gas storage because it's a fixed roof. The roof is insulated. That's a plus, so I lose less heat. And the mixers are very efficient because it's just one central mixer of 50 kilowatts that is mixing the entire digester. Pancake, we have the integrated biogas storage as described. We have integrated H2S reduction, later more on that. Lower static loads on soil. So I get away with simpler foundations often, depending on the geotech conditions, and can be easier to clean. We do both in epoxy coated or concrete, and for the pancake digesters we have stainless steel as well. little impression from concrete tank and constructions. Usually, concrete is a good option. It depends really on the project, what makes more sense, of steel, epoxy coated, or stainless, or concrete. Forming or form cost play a big factor. So it depends if those forms are already available or if they have to be fabricated for that project. If you are tight and you have to go into winter construction, concrete is not the best choice. So here in this picture, we see winter construction. So below that foil, everything is heated. And concrete was poured in winter time. This year is in a seismic zone. It was insane amount of rebar in those digester walls, and it's 16-inch walls. And then in Europe, there are some forming technologies often used in Europe, smaller forms that you build a ring off, and then you pour the tank in layers, ring by ring. And then there are some companies as well that offer forms that remain in the digester wall. Steel tank construction. So this is how we build our stainless steel tanks. We build the stainless steel panel ring first, and then we lift it up and build the next one below. The first ring takes 5 days roughly because there's a little bit equipment attached to it. And then the other rings, 2 days. We do the installation at the inside, and we insulate the tank with a liner at the end. So there is no sealant in between the stainless steel panels. The tank becomes watertight by use of a liner. And then at the end, we have to install the EcoNet, which is for desulfurization, and the roof. That overall takes 40 to 45 days. But if you build, let's say, 4 digesters, the crew that erects the stainless steel panels can start with the second digester while on the first digester, the insulation is being installed. So it doesn't take 4 times 40 days. The cold commissioning takes 10 days, and the hot commissioning for dairy manure around 45 days. Modular design, very important. We try to combine crucial technology functions in one container. So this is pumping, heating, and the electrical cabinets with the MCCs, and then a couple of other smaller technical components for washing the windows of the digesters and O2 injection. We try to do most of the fabrication facilities in a controlled environment, and to make it easy to install the digesters, the tech containers, and all the components on site. A little bit about gas storage. So just an example here, that's the biggest tank that we have in the pancake style. It's 112 feet diameter, and the gas storage in that roof is 120,000 standard cubic feet. So it means if I have a gas production of 200 SCFM, I have 10 hours of gas storage. And that's significant because you can run the biogas upgrading system at an optimal speed with lower electrical consumption at highest efficiency. It's a little bit like a car on cruise control, and you can bridge times whether you have a good shut-in or where you do planned maintenance or unplanned maintenance as well. 10 hours, you can get a lot done in 10 hours, and you don't have to flare.
Nils, can ask one question here. The question came in about mesophilic versus thermophilic. What is PlanET's preference? And can you speak to thermophilic and ammonia toxicity and process controls compared to mesophilic?
Yeah, the next slide after this one talks a little bit about mesophilic, but I will get back to that. Yeah.
Okay.
So mixing, very important. Different types of active mixing and CSTRs. We at PlanET, we use mechanical mixing, internal mixers, external shaft mixers, and as well on the video you see pedal mixers that are used in very high solids feedstock that tends to build crust, and fibrous feedstock where you have to break that crust from time to time. Active mixing is very important to distribute the food and the trace elements, to support temperature stability, to distribute the gas within the digester, and therefore the overall health of the methanogens and other critical microbes. You prevent settlements that would reduce active volume to a certain extent, right? crust formation. So that's very important. There are other technologies as well, active mixing technologies, hydraulic and gas mixed. They have their advantages and disadvantages. We don't use those, but we are constantly evaluating if it makes sense to integrate them into our portfolio. So temperature control, that's a key one to keep it at the right temperature. We do mesophilic, so in the range of 95 to 104 Fahrenheit. Our equipment could do thermophilic as well, so we could run it on thermophilic temperatures. Generally, we design for mesophilic because the gas production is close to thermophilic. It's pretty close, pretty good, but it's a fast, stabler process, and it's easier to control this process and to maintain a constant biological processes in it. So that's why, to answer your question, Paul, or the question of the participant, we designed for mesophilic digesters.
Okay, so let's just put a pin in that. So thermophilic, you believe is more costly or not as strong technically or not as robust?
I mean, you can design, I mean, it's never that one technology is worse than the other. We are constantly evaluating if on a certain feedstock and a certain project setup, thermophilic would make sense as well. But so far we haven't done it. So the main reason is that the process is more challenging to control and in cold areas. That's another factor. The temperature difference of within the digester to the exterior is larger, right? So you lose more energy as well, and that has to balance out with the gas production, OpEx versus revenue as well.
Okay. One other question came in on materials of construction.
Mm-hmm.
Do you use stainless steel very often, and specifically duplex stainless steel
Yes.
in the tanks or the mixers or the pumps based on chloride levels?
Yeah, so we use duplex stainless for those pretty often. Yeah, so most of the digesters in the US that we've built in recent years are stainless steel. There are some concrete digesters as well, and some epoxy coated. And yes, we use it because we have a good supply chain for that type of steel, and it's very, very robust and corrosive resistant.
Okay, thanks.
But we evaluate for each project what makes more sense, so it doesn't have to be stainless steel. So regarding the heating, insulation is first line of defense, but very important. 75 to 80% of the heat that I need to heat the digester goes into heating up the substrate. That's very important to know, because if I improve the insulation, I only tackle the 20% that are required to keep the temperature in the digesters. And that varies over the season, obviously, on cold winter days. That's a little bit higher, but it never goes over 30%. Very important. Then regarding heat exchangers, so we use in-tank heat exchangers. We have different technologies, stainless steel pipes or heating racks. They're immersed directly into the digester and allow for a very good heat transfer, but you have to design them, obviously, that you don't need to maintain them or to do maintenance unless for the normal tank cleanouts. In contrast to that, another option is external heat exchangers. They're a little bit less efficient. Some technologies have issues with clogging, but the big advantage is you can maintain them outside of the digesters.
So to speak to the fouling a little bit, question came in. Do you see fouling of the heat exchangers commonly in your projects?
Not very much. So our control system, so we measure the temperature in the digesters, and then the control system adjusts the glycol temperature and the heating circuits in a way that the differential temperature is as small as possible to avoid baking of manure, for as an example, or substrate on those stainless steel coils. So it's manageable in between the tank cleanouts. A little bit about H2S. So we're at minute 29. I have a couple of slides. I hope I can continue a couple of minutes, Paul.
Yeah, we're fine on time.
Okay, good. So very important considerations, H2S. It's a very toxic gas. It's explosive. It's heavier than air, so it collects in low-lying enclosed and poorly ventilated areas, and it's very toxic. So you don't want to expose to it in low concentrations, but in high concentration, it gets very, very quickly fatal, especially if those concentrations are above 1000 ppm, and those are levels that we have in digesters. So it's critical to reduce the H2S. In addition to health and safety, it's always good, or the best way is to reduce the source as much as we can. So it's important to reduce that H2S. And PlanET has in the CSTR digester 3 levels, or 2 levels in the digesters, 1 then post-digester to reduce the H2S. The most cost-effective one is this one here, is to use aerobic bacteria by oxygen injection into the interstitial room between substrate and digester gas membrane to reduce the H2S, and that works pretty well. So we inject oxygen, and yeah, we reduce the levels in the range of 1500 ppm, and it's very cost effective. The capex is not expensive, and the opex not as well, right? The oxygen is generated or concentrated on site by oxygen concentrators.
How do you
And
feel
then
about ferric salt addition for H2S control?
ferric chloride and micronox?
Ferric chloride specifically came in as a question.
Yes, that's the next slide. The question is always for the next slide. That's
Yeah,
amazing.
yeah.
Okay, so
Good
I'm
question.
jumping to the next slide in a second. So what you see here, the elemental sulfur is dropping. Yeah, you've seen it here. It drops down into the digestate and then is extracted with the digestate. So that's a very cost-effective way and the cheapest. But it's obviously not exact science, right? You cannot exactly define how much it will be reduced, and you have to be careful with the oxygen injection. It has to be controlled against what's in the upgraded gas, that you don't have issues with the grid specification. So the second lever is chemical. So what we use in most of the plants and what we recommend in most cases is Micronox, is an iron hydroxide that is less corrosive than ferric chloride. It requires more time, so it's more an overall damping function. It's easier to handle and it's easy to storage. The other option is ferric chloride. So we have technology for that as well, and inlets. It stores directly into the tank. It's very corrosive, so you have to design those pumps and pipes very well, and it's a challenge to avoid a big mess. It often doesn't look very nice, those areas where ferric chloride is injected on not well-operated sites. The big advantage of ferric chloride, it's immediate. The effect is immediate, and you can tackle spikes. So it's reacting far faster than Micronox. And we have plants as well and operators that use both. We have a plant in Lethbridge that has a level of 50 ppm post those two Micronox and oxygen injection, and you only need to get roughly 50 ppm out of the gas with activated carbon in the biogas upgrading unit, which is the most cost or most expensive way to do it. So you want to have that level down. Considerations for operability, and I have only 5 slides left, so I'm getting close to the end. So it's very important to account for variation in feedstocks and disruptions due to the output offtake systems, so solid handling, BOP, and so on. So you have always to plan with some sort of buffer capacity in the process. Design for future expansion if required, but very often it's required. Ease of maintenance, very important. You want to make the life of the operators as easy as possible. So space for work, redundant systems. It's very frustrating if you don't have space to do the maintenance, or if you cannot hoist heavy components. Health and safety is very important. Ventilation, gas detection, emergency shutdown as examples. And very, very important to spend time in the design in the early phases. In operation, real-time monitoring systems are important, that you always see the critical parameters in addition to testing. Automated control systems to make your life easier, and we're looking a little bit in AI on that one as well, and data analytics to predict any upcoming issues. Very quickly about biology. So you have to monitor what you feed into the digester. So it has to be the appropriate feeding range, but you have to be concerned with the quality as well. You don't want to feed inhibiting chemicals like antimicrobials or heavy metals. It has to be the living space of the bacteria has to be consistent, and you have to keep the chemical or certain values for various chemical reactions in the right range: temperature, nutrients, pH, alkalinity, and so on. So now the loop closes a little bit to what I've explained in the beginning. Just want to give a quick example on FOSTEC, and Bernie might talk more about it later. So just very high level. FOSTEC is actually German. So FOS stands for volatile organic acids, and TAC stands for total inorganic carbon or alkalinity, buffer capacity. It goes under different words. And what's happening here, I'm analyzing the balance between the bacteria that are producing the acids in the early phases. And as I mentioned, very fast reproduction times with the methanogens that produce the alkalinity. And the methanogens like pH around 7-ish, those guys here 5 to 6, right? So they're interested in producing acids. And I have to keep that balance. And I can measure if I'm feeding, and feeding is the biggest lever on that. I can mostly solve it about the feeding quantities and feeding rates. So the feeding controls this. And with FOSTEC, I get an indication on the biological health of the digester and if I'm feeding correctly. So there are a couple of scenarios. One is if the FOSTEC is higher than 0.5, I'm overfeeding. So what's happening when I'm overfeeding? The volatile organic acids are increasing, so pH is decreasing. The alkalinity is decreasing because the methanogens get unhappy and produce less alkalinity. And the consequence, the CH4 is decreasing and the CO2 is increasing. So I have an overfeed situation. I have to stop feeding, I have to reduce feeding, and that normally solves the issue. If that's not done with reducing feeding, I can add alkalinity as well, but in most cases, it's not required. The opposite is, and it's an interesting effect as well, I'm underfeeding. So what happens when I'm underfeeding? It lowers the gas production as well, but very interestingly, I get a higher methane content. And so how does this happen? It happens because there are two types of methanogens in the digester. The dominant ones are breaking down the acidic acid, so the third level products, let's call it, into methane and CO2. And the other type of methanogens can produce CH4 out of hydrogen and CO2. And those are then dominating because they don't need the acidic acid to produce CH4. So we recommend to test those parameters pretty often. So FOSTEC twice weekly. pH is measured along with FOSTEC. Ammonia depending on feedstock. And then very important as well, conductivity. So why conductivity? Conductivity is measured in microsiemens per centimeter, gives an indication on the salinity in the digester. And salinity can be harmful for bacteria because it's creating osmotic pressure in the bacteria. So all those I want to have monitored. We can do those testing for you, but you should have some equipment, at least for the FOSTEC on site as well, that you can do regular FOSTEC testing. But there are tests that are better done in a laboratory, and we are offering those as well. That's the biological side, and just a glimpse. On the maintenance side, the operators, we support the operators with checklists and advice. It's like a pilot, right? You have to automate your checks to make sure that you get all the information on a daily basis, that you can predict or see early on if there are issues occurring. This is just an example for a daily maintenance checklist. We have more weekly, monthly, and then we come in as well for regular maintenance, and we offer those that support. This is another snapshot on a winter maintenance checklist that you should do before the first frost. So that's very important as well to do this. And then obviously on all those stages we support, and then there are cases where you should definitely call experts with the right equipment. As operator, you don't want to work in SCBAs and with SCBAs and do procedures where you need a lot of people to maintain safety, right? So that's where we come in. And now, yeah, I'm already at the last reference slides. So I would like to, Paul, you will share those slides. It's a couple
Yeah.
of plans, and yeah, would like to open up for questions.
Definitely getting some more questions about materials of construction. So on tanks, again, we were talking about corrosion and chlorides. So how do you decide concrete versus steel tanks? Just walk through the thinking, the metrics there of how do you pick stainless steel or glass lined tanks versus concrete?
Yeah, so concrete has a couple of advantages. It's relatively easy to construct with local companies. As I said, the forming costs are a factor, so you have to get some quotes. One bigger advantage is that the mixers that are wall mounted, I can install them right in the wall. So I can show it here. Those mixers here, it can be installed right in the wall on a steel tank. I need to install them. I cannot induce the loads into the wall, so I have to install them in a frame that has a separate foundation. So that's more expensive. But generally, there's no, in terms of functionality, there is no real advantage of concrete over stainless steel. You can design both in a way that it works well. And then, yeah, winter construction, that's another consideration. If you have an area where you have a long winter, you have more flexibility if you use steel.
So back to the thermophilic question. One of the guests argues that thermophilic systems should be smaller. The higher temperature leads to lower residence time and maybe lower capital cost. Is that anything that you've seen?
Yeah, I'm not contradicting that. Yes, the thermophilic are so if you run it on a thermophilic level, the retention time is shorter. So the time retention time you need for the same gas production is lower. So it leads to smaller digesters, but you have to counterbalance that with the OpEx cost that are required to heat the digesters, right? So it's always those three drivers. It's revenue, so biogas production and what you get for it, how much money you get for it, versus OpEx and CapEx. And when you bring all three together and do investment calculations, then you can define what's the best for you. Considering as well how many operators you have available, what the experience is, right? Do you want to have that effort to run that system that's a little bit more sensible or to disturbances? So yeah, but there is no right or bad way, but we're doing generally mesophilic.
So we have time for one or two more questions. The main presentation is over. At the top of the hour, we're going to have Tim from Teche come in to talk about pre-processing. So if you need a break, take a break. But we'll stay here while we have Nils for a couple more questions. So back to internal versus external heating. Do you ever do external heating, or do you always have the heat exchangers inside the tank? And what is that thinking again of internal versus external?
So we always have internal heating. We are evaluating constantly the external heat exchangers as well. We are using external heat exchangers for heat recovery. So glycol in some cases. But we don't use heat exchangers so far on substrate. It really depends on the technology that you use. There are some technologies where the diameter is pretty small, and then with feedstock, certain feedstock types can cause clogging there. So I'm not saying it's not a good solution or it cannot be done, but so far we are mostly doing in-tank heating.
So a question came in about your presence in India. Do you have an office in India? Do you support India?
We have projects in India, and we see a future market in India as well, and we have recently founded a presence there as well. Yes.
So if somebody wanted to talk to PlanET about India, maybe they could shoot you an email.
Yes, and then I will refer them to the right contacts within the global company. Yeah, of course.
Is there a list of lab equipment handy that PlanET would say, here's a one pager of all the equipment that you should have in a properly operating biogas analytical lab?
Yeah, I will check with our biological manager here in North America, Tim Alick, and then if there's a concrete question, I'm happy to connect you to Tim as well.
Okay, if such a list was available, that
Mhm.
would be welcomed.
So recommended on-site
Yeah,
laboratory
so if you had a
equipment.
lab at
Yeah.
a digester, what equipment would you buy for TS and VS and pH and
Yeah.
ammonia?
Yeah.
So here's a wonderfully fun question. So tank failure rate, lovely question. We really enjoy this one as an industry. Can you comment about digester tank failures?
I mean, we do. So we don't have any catastrophic failures in that sense, but sometimes during leak test we detect leakage that has to be fixed. So that's why we do leak testing before we actually fill the tank with substrate. And there are different versions of leak testing and different heights. Some clients do fill the complete tank with water. There are options as well to do it 18-inch and then to check the seams separately, the welding seams of the liner. But that's very important to do leak tests before I actually fill it with manure. Yeah.
Okay. Very well. Still a few questions unanswered, but I think we've covered a lot of ground here in 50 minutes. So Nils, just wanted to thank you for your time. If people have additional questions, you can send them to Nils or me. And so we're going to take a few minute break here before we get to Techen and waste pre-processing. So the CSTR segment is adjourned. Thanks again, Nils.
You're very welcome, and thank you for having me.